good, my statisticians? This is Professor Sampson from PS I Love Math, back with another statistical banger. As you can see, I'm so excited. Because we are going to do our last set of confidence intervals up in here. So we're going to talk about estimating population variance. And we don't do that often, but when we do it, it's important. Think about it like this. Things shouldn't vary from an assembly line to assembly line. So something important like car parts, you want to know that that part that came off is within the same variation as the part that came off before. You don't want parts of your engine coming off at different variants. So companies like that use this interval to figure out the variances to make sure that each part that comes off is within the proper variation, and if it's not, then what they do is they have to go back and adjust the machine. And this is with anything. I said carts, it could be anything with healthcare, any of those machines that we use on a regular basis. So that's what we'll be doing, confidence intervals, basically estimating population variance. But we are using a new chart. Before I get overexcited into this, we have a little bit of lecture to do. This is going to be a longer video because we learned a new chart and I need to make sure you know how to read it. So that's about it. We need to get into it. Don't forget to like, comment, and subscribe. So of course, we're going to be estimating population variances. So let's talk about our new chart. Our new chart is called chi, not x squared. Chi squared. It's called the chi-squared chart. And the following properties are the properties of a chi-squared distribution. Unlike a normal distribution and a t-distribution, these are not symmetric. So a chi-squared distribution is a continuous probability distribution, and it's defined by its degrees of freedom. Comment down below if you remember how the z chart and the t chart are defined. This is defined by degrees of freedom. Comment down below if you know how the other two charts are defined. A chi-squared distribution is skewed right. So when you're reading it, you're reading right, skewed right. The values of chi-squared are always greater than or equal to 0. So no negative values for chi-squared. Unlike you can have a negative t or negative z, for chi-squared, no negative value. The shape of the chi-squared distribution is completely determined by the number of degrees of freedom. You know degrees of freedom from the t chart because we use degrees of freedom when we're reading a t chart also, n-1. And as the number of degrees of freedom increases, the shape of the chi-squared approaches a normal distribution. Hey, the mean of the distribution is equal to the number of degrees of freedom. The mean of the distribution is equal to the number of degrees of freedom. And check this out, the variance is equal to 2 times the number of degrees of freedom. How you like them apples? That is our chi-squared distribution. And now I'm going to put up the formula. So we can have confidence interval for population variance. And there's the formula, n-1 times s squared all over chi-squared. Alpha over 2 is less than, the variance is less than n-1 s squared over chi-squared 1 minus alpha over 2. That's the variance. If we wanted the standard deviation, remember the standard deviation is just what? The square root of the variance. So as you see, the other formula is the same. Only thing we do is take the square root so we can remove the square, so we just take the square root of both sides. So there's both of the formulas.
What the hell are you talking about?
So here's an excerpt here from the chi-squared chart. Now I'm going to show it to you in a bigger form. But just to show you how it works based on our last slide, how do we find these boundaries? So let's just do a quick example so that you can see how to read the chart. And then we will do a couple more examples where we put it all together. So let's say if I gave you that n is equal to 17 and alpha is equal to 0.10. Now how do we go about finding the two boundaries for chi-squared? So the difference between z, right, and chi-squared is that z was symmetric. So you could just have one and just figure out the other one. So if this was negative 1.96, then this was positive 1.96, right? So that was a z distribution. A chi-squared distribution is not symmetric. It's right skewed. So with it being right skewed, we have to figure out these boundaries here. We have to figure out these boundaries here separately. So as you see in the last formula, you'll have chi-squared alpha over 2, and then you'll have chi-squared 1 minus alpha over 2. That's how you figure out chi-squared. So in our case, we're going to have chi-squared alpha, which is 0.10, 0.10 divided by 2, 0.05. Here's 16, and we're looking for 0.05. Go over until you find 0.05. So here it is right here. So that is 29.296. Then we do the same thing here. Remember, this is chi-square 1 minus 0.05 over 2, right? Which we know is chi-square 0.10. So what's that going to be? 0.95. 1 minus this is 0.95. Now we need to look up 0.95. 7.962. T and chi-square are both rounded to 3 decimal places. Why? Because that's the same number of decimal places in the chart. You don't round differently from the chart. So hopefully you understand we got these two here. And those are going to be our two boundary numbers when you're looking at a chi-square chart. So now we can have fun. Let's move on to some examples of putting this whole thing together and finding our confidence interval. So let's get this party popping.
Oh my God!
A company is testing 63 randomly selected compact fluorescent light bulbs to see how long they last. The study results show a standard deviation of 121.4 hours. Construct and interpret a 99% confidence interval for the true standard deviation for the lifetimes of the compact fluorescent light bulbs. Started with writing our knowns. The first known is N, because we have tested 63. N equals 63. And from that study, the results were what? Shown to have a standard deviation. So that's why it's S, because it's the standard deviation of the sample of 63 of 121.4. And last, the confidence interval is 0.99. So here's our formula, because they said find and interpret the interval. So here's the formula for standard deviation. And I always check, we need N, we need S, and we need chi-square. So let's figure out our chi-square. So chi-square is alpha over 2. We need to figure out alpha. So alpha is going to be equal to 1 minus 0.99, which is 0.01. So 0.01 over 2, and alpha is going to be equal to what? 0.005. So x chi-squared 0.005. I'll give that in a minute. And we might as well do the same thing here. Chi-squared is going to be 1 minus 0.005. Right, so here we're looking for chi-squared is equal to 1 minus 0.005 or 0.995. Let's switch over to our chi-square table. Our degrees of freedom, well, if N is 63, then our degrees of freedom is 62. So look on your chi-square chart as I'm doing. Now, if your chi-square chart doesn't have that number exactly, you have to take the lower number, not the higher number, the lower number, because we want to err on the side of caution. Don't want to overestimate. So we're going to use 60 on this chart that I have. So for 60, I was looking for 0.995, which here is 60 all the way across. So I'm looking for 0.995, which is 35.534, 35.534. And also I need 0.005. 0.005 is the last one, looks like 91.952. So now I have my numbers, and now all I need to do is just like any other one, is plug it into my formula. So I have the square root of 63 minus 1, 121.4 squared, all over the chi-square alpha over 2, which is 91.952. That's less than sigma, which is less than the square root of the same thing at the top, all over. Now this is minus 1, so 35.534. Remember, rounding rule is the same as it used to be. You can't go any more in detail than what we're given. We were given this. Sigma is rounded to S is rounded to one more decimal place than is in the data. There's no data, and we already have something given to us, so this one is going to be rounded to 1 decimal place. So we have all our numbers in, and now we want to go to our calculator, right? And we want to run to our calculator and put this in and find some place to put it. There is no interval for standard deviation. So you have to exactly know now how to put things into your calculator. You're going to have to put them in by hand using the numbers that you have listed here. So I'm going to go over to the calculator and put these numbers in.
Can't nobody tell me. You can't tell me.
63 minus 1. Now I could have put 62, but I'm just going to plug it in exactly the way it is. 121.4 squared all over 91.952. 2. So I hit enter and I get that. Now, this is the part about knowing how to use your calculator. I don't want to plug all that in. I can hit the up button and go up and pick up that exact one, but you need to make sure it's right. And the only thing I need to change is the bottom. So I can just hit left until I get to the bottom. I can just clear out the bottom and put in a new number for the bottom, which is 35.534, and hit enter. Now I have my two ends. So it looks like one is 99.7 and the other one is 160.4. So let's put that down. 99.7 is less than sigma is less than 160.4. So we have our confidence interval, and now we need to interpret it with 99% confidence. The standard deviation for the lifetime of compact fluorescent light bulb is between 99.7 and 160.4 hours. So that takes care of that. So we've done everything that we need to do with that. I know this video is long. I'm like DJ Khaled. And another one.
You're joking. Not another one?
So let's do one more, which is a little different. This is when they're giving you data, so you can see how much work you have to do if they're giving you data.
Oh, for God's sake, I can't stand this.
What I've done is, here's the question. Consider the following sample data. So now you're given data. Build and interpret a 99% confidence interval for the population variance. The last one we did was for the standard deviation. That's why I wanted to do this one with the population variance. As you can see, the formula is over there. So I'm going to go to stat and edit, and I'm going to put in the data. Feel free to put in the data with me.
Whoa, whoa, I press the button and the doors go off like, whoa, that money clip us not a new, now looks like, whoa, upgrade her diamonds, now her girlfriends are like, whoa, 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 whoa.
We go to stat, calculate, and let's go to one variable statistics first. My information is in L1 as it's been throughout the course. And now we have what? We have our, what are we looking for? Well, one thing we're looking for is our N. N is equal to 15. So we have N. Now we need the variance of the sample. Let's go back to our calculator and get the variance of the sample. Hopefully you remember how to get the sample variance in your calculator. It is not sitting here. So where do we go? We go to VARs, number 5, statistics, and then we choose what we're using. So we're going to use what? Sample standard deviation squared. So we're going to see the sample standard deviation is right there. And then we're going to hit it, and then we're going to square it, hit the square button. And now we have that 0.0426. However, let's take a look at our information. Now we put in data this time. Remember, our data was what? Our data was 1 decimal place. So we have to do one more than the data is given to us. It just gotten the standard deviation and then squared it in there. Okay, 2 ways to do it. This is going to be 0.04. Okay, because I already squared it, so I don't have to square it again in my calculator. Now, some of you can get S and use S and then square it in there. I do it in advance. Okay. S squared, 0.04. Okay, so let's put this all together. We have to get our chi-squared value. So we're looking for chi-squared alpha. So that's going to be 0.01 over 2. Again, chi-squared is equal to 0.005. And then this chi-squared is going to be 1 minus 0.005. So that's going to be chi-squared is equal to chi-squared of 0.995. And our degrees of freedom is going to be 14. So we need to go to 14 and find 0.005. And 0.995. So for 0.995, I have 4.075005. We have 31.319. Okay, so now we can plug these into our formula. 15 minus 1. I already did S squared. I don't have to square it again. So that's the only thing you might want to check into. All right, because if you do it this way, you might want to do it the other way. Let's go back to our calculator because I don't want you to get confused. So if we look at our calculator, right, stat calc, one variable statistics, right, we had S, and S was equal to 0.21. So whether you put in this that I put in, or you can put in this 15 minus 1 times, what's that, 0.20, then square that. But if you square it here, don't square it here, and that's going to be 31.319 is less than variance is less than, again, 15 minus 1 times 0.04 all over 4.075. And you notice I don't have to square. I already squared it, so it just makes my calculations easier. I have that side. Again, I just go up here, grab that, go to the bottom, just clear out my bottom, and then hit in 4.075, and then hit enter. So now I have both in. Now remember, when we put in our data, we had 1 decimal, so we have to go 1 more than the decimal than the data that we have. So our answer is going to be 0.02 and 0.14. So 0.02 is less than the variance is less than 0.14. And I'm going to just write it out. I'm not going to count. We are 99% confident that the population variance. We don't have any information of this, so it's just is between for whatever this data is, 0.02 and 0.14, sorry. And that's the full problem when you're given data. So either way, do it. This is a long video, but I think it was worth it. So I hope you liked it. I had fun doing it. And that will conclude our confidence interval section. Please don't forget to like, comment, and subscribe. Look at the other 2 videos on confidence interval. And I am Professor Sampson from PS I Love Math, and I'm out of here.
If you want love, look somewhere else. He'll find